But as I mentioned, explosion is explosion, and this is underwater explosion. That makes it quite different from air explosions. That's what the application would be, as I mentioned, for military use. But you know, in underwater, there's when the gas leaks, the pipeline leaks, then gas gonna come out, then it could generate the explosion also. But maybe scale may be quite different. But someone, you can see me there, right? Do you see me? No? I see you, and I see small picture screen there. I can see myself here. No?
Yes, I can see you right now.
Okay.
I want you to turn on, so I can see screen and you.
Okay. Okay, that's good. So application-wise, explosion is like a transient phenomena. Remember, transient phenomena is not the steady state phenomena. Something like in the vibration mode, the vibration is just repeat by itself. Well, especially rotating machinery, it repeats. So that's kind of the steady state. But shock, explosion, the situation is quite different. Once occurs, never repeat, never be able to repeat. You spend the millions of dollars to set the sensors, all the gauges, you set all the explosive on site, then bang, then all the monies are gone. That you can't take it back. Or if you have a mistake, then you can't repeat the same thing. So really need careful settings, considerations, lots of study has to be done. So explosion falls in the category transient phenomena. Okay. So this week, well, Monday, Wednesday, a little bit last week, I'm giving you a little bit on the overall naval ship shock effect. Then we look into a little bit on the excitation, which is in this case is explosion. The next item we look at is what's the purpose of all doing this, to really getting into the computation or measurement of response, right? So when you say response, we discuss a few different things. Then we're looking into the modeling. So I talk about the modeling and simulation, and the system nowadays we are dealing with really complex system. So there are class of the problem. Of course, you can get a closed form solution, then all the basic phenomena, dynamic behavior phenomena, you can really study using the closed form solution. It's a theoretical solution, but a lot of time to really get the result out, then you have to really use the slightly different modeling technique, using the finite element approach or finite difference approach, and nowadays there's a lot more. But the popular modeling technique is using the finite element methodology. So you are learning, as I checked before. Who is missing today? 3. Gusto, yeah. More. Well, anyway. Oh, Yongwon and yeah, they're out there in Changwon, so that's right. So it's all Kent. So here I talk the other day about the experimental modeling. For the experimental modeling, I mentioned about the DDAM, which we're going to study toward the end of the semester, dynamic design analysis approach, which is what the Korean Navy is also using it to really check out whether the shipboard equipment would survive or not. So has to conduct the analysis. So, but old methodology. So I'll tell you later when we discuss the DDAM what other options you have. So we have a transient, direct transient analysis to conduct and all that. But DDAM, remember, dynamic design analysis method, good method to look into the details on the survivability of the shipboard equipment. Shipboard equipment's survivability is the most important, because if such equipment cannot survive, you got a problem, because the ship itself is a sitting duck. So it's like a cruise ship. Because if shipboard, all that brain is gone, then no reason the ship is sitting on it, on the water. And another couple things I mentioned to you is, remember this, SSTV and FSP. In the video clip, you already saw the SSTV there. Submarine shock testing vehicle. You may not remember, but you saw it, because I saw it there. And FSP, you saw it, floating shock platform. So this is for, both are also for testing the shipboard equipment. So FSP is simply barge. Barge is the floating shock platforms. That's what, then you put the shipboard equipment and put the charge and bang onto it. Okay, so if you stay until the 2013 at least, you are able to see actual explosion testing. We're gonna blow up so-called Hanuri ship. So the guys that take over got it free of charge, which is kind of old, the training ship. But we're gonna study. Some of you may involve in modeling and also simulation, and also go out, blow up. So quite a few different organization is going to get involved. The ADD, Agency for Defense Development, and Korean Institute of Machinery and Matters, and of course KAIST. We're gonna be the main organization, vice versa. So that I want you to remember. Nuclear, you don't have to worry about it. And I talk about the submarine penetrator. Also, surface ship has a penetrator. Penetrator means it's really right on the hull, and there is a big chunk of mass attached on it, and they can take water in and discharge the water out. And of course, you will do the example problem sometime later in October, maybe early November. That's what you want to do. Okay. This is like experimental modeling with that name. Mathematical modeling is rather trying to have closed form solution to get the response. Again, for mathematical modeling, you can use the word theoretical and analytical modeling. Again, air and the water environment. For the air situation, for penetration, it involving fragment, shape charge, air blast structure responses, few different methodology to do. Air explosion and underwater explosion, one of the main difference in there is air explosion has a fragment. In Korean, it's a papyeon. Because air density is very low compared to the water. So when explosion occurs, the bombshell just divided into small pieces, and with a high speed, it just flew all over. So that's a typical air explosion. And the shape charge is one of the weapon, which is really like a large, you can say large bullet, or missiles is like a bullet. Then right inside, of course, it has gunpowders and all that. At the middle, it has like a sharp spear kind implemented in there. So when people shoot toward the tank wall is pretty thick. Then usually just the bullet itself cannot penetrate the tank wall. Is very thick. So they have a shape charge in there. So not only when it bang on it, it generates penetration at the same time, explosion at the same time. Like inside, it has a very good size spear type, which will just shoot right from inside toward out. So it's multiple effect. So it just goes through right in. It kills whoever contains in the vehicle. So the water structure medium interaction here, what I'm going to cover is Taylor flat plate theory. Taylor flat plate theory I'm going to cover to show you clear understanding of fluid structure system, fluid structure interaction phenomena. What does it mean, fluid structure interaction phenomena? This is a hull, okay, and ship hull, okay, or submarine hull. When the shock wave hit it, then what happened? This is a flexible, it has a stiffener. So when shock wave hit the hull, this will cave in, right? This will cave in, but this has elastic property. Of course, it could have elastoplastic kind of the property or kinematic properties and all that. But after it deformed, may not restore the whole thing 100%, but majority will restore and move back. When it hit it, this hull will move back, then it will restore, then it's going to push the water out there, right? When it hit it, this hull will push it back. But the shock wave is a thin, you can assume a thin shock wave front, but it has a tail in it. In other words, shock wave at the beginning when it hit it is a Pmax, maximum pressure, but as it passes by, the magnitude of the pressure, it decreases kind of exponentially. So it's going to hit back. This is interaction. Okay? So, of course, I'm going to repeat and study quite details later when the time comes. But I always give you some quiz, especially when your eyes is getting closed down and getting tired. So I give quiz. Okay? So this is how to resist under shock. If you can make infinitely thick, this will never. Doesn't matter how big your shock wave comes, then this is perfectly safe. Probability of survival could be 100%, right? Then whoever make them that, maybe 10-meter thick hull, the ship will sink, right? So whoever make them has no way to run the business. They have to bankrupt. So they have to live with the probability, some probability of the failure. Right? Some probability of. If this is infinitely rigid, right? Let's assume this is infinitely rigid. And the shock wave, let's say 1,000 PSI. PSI is the unit that US is using, pound per square inches. But in the metric system, what do you have? What unit do you have? Let's say megapascal. Let's say you have 10,000 megapascal pressure is coming hit. But Yongxin is putting the hole in the very thick the hull, then sitting in there. If I just bang onto shock wave, bang onto it, what kind of the pressure, or simply speaking, this infinitely rigid wall would experience? You follow me? This is rigid, okay? Rigid means doesn't move. So I have a shock wave whose magnitude is 10,000 megapascal and hit. Then what would be the pressure that this, the rigid wall would experience? Guess, Lee?
The man absorb the whole pressure.
This is 10,000, this is infinitely rigid, doesn't move. I'm sitting here. Then bang onto it, what kind of the pressure I would experience? I'm at, let's say just a hull, this rigid wall. Anybody? Who said the 20,000? Because I gave a quick 3-hour kind of the lesson during the summer. If I hit it, the answer is 20,000 megapascal, is twice of the shock pressure. It's strange, isn't it, right? So the reason is this 10,000 megapascal pressure will hit. Naturally, 10,000 megapascal pressure will experience, right? But I didn't say the shock wave does not absorb everything, assuming everything reflected back. Bang, then reflected back. That assumption I have to give you. If everything is absorbed by the rigid wall, then that's it. But bang, all the wave, shock wave will reflect back. That's assumption. then when it reflects back, to be able to reflect it back, you have to, this shock wave has to kick the wall. Otherwise, it's not going to reflect. One goes in, when it comes out, that wave, pressure wave, has to kick the wall. That takes another 10,000 psi to kick it. Then, if you add it together, that's a 20,000 megapascal. You'll learn more. Sometimes the shock is against your common sense. Another one, usually I give at the beginning, this is your ship. This is neutral buoyancy. It's really floating right on the free surface, right? And explosion, I put the charge right below, then I put the charge there and let it detonate. Then what direction this ship gonna kick off? Of course, vertical direction, right? Shock wave, I have a bomb at the bottom, kick. So this is gonna go up, right? Agree with the common sense, right? What happens if this is ship? What happens explosion occurs here? What direction this ship will kick off? Will it? Based on your common sense. Bang! Then this guy will flew these directions. Then it will capsize. Everything will die. But God loves the world. It shouldn't be that way. So wherever the explosion locate, this ship always kicks vertically. So this is strange, right? But this is due to, this is called the incident shock wave. Then when the incident shock wave hit the free surface, it generates the surface reflection wave. It's going to go that way. This is a free surface, hit it, then it will bend. But that surface reflection wave is so-called the tensile wave or rarefaction wave, which is particle motion takes in downward direction. At the same time, the particle takes the above the water, and the reflection wave, acoustic surface front of acoustic reflection wave goes that direction. It's called the tension wave. I'll spend some time on that in chapter 2. So that's against our thought. Okay? So there are a lot of such a thing. So then you have to really pay attention, then you will really learn the phenomena pretty well. I'll mention about the DAA methodology to look at the fluid structure interaction for explosion situation. We don't use this technique much nowadays because computer science is getting so big. We have in our department we have high performance computing system which is rather big, 256 CPU. That's quite large. 256, it's small but large. But now we are complaining that's too small. So keep saying we need a larger one. We need a larger. So it's endless wall. But we have a pretty good computing capability in OSE. So we use so-called the arbitrarily the Lagrangian and Eulerian methodology to conduct the fluid structure system. And this nonlinear, this is all approximation. We'll talk about this bulk cavitations and all that. And this but WINET, this is too old, so we are not going to really concern about that. So some are old, so we'll delete. And historically it's worth it, but practically not worth it. And to solve complex problem, then you need some computer code to solve for closed form solution, to get the closed form solution for simple problem. Of course, you can do the coding yourself as a part of your degree program. That's also good idea for you. Really you solve equation mathematically, then you can really solve that using like a MATLAB or Fortran or C++, whatever. You can code it, okay? You can write the program, then you can solve it, get the result out. But if it's a rather simple problem, you can do. But if it's a little bit complex, okay, then you have to go through the MNS. So my students in my lab, we do quite a bit computation using the commercially available software. Computer code means the software, which developed for a long time, like LS-DYNA code. We're using quite a bit. That's initially start developing in 1970s and really building up, maintained for 40 years by the John Hallquist in Livermore, which is really, I count one of the best code. You can add options into the LS-DYNA code, and it's a very powerful code. That's why we are using it at the present time. But USA code is also very good. There's the underwater shock analysis code developed by Lockheed, the Palo Alto Research Center a long time ago. But nowadays, I don't even use this portion. LS-DYNA is what I'm using it, because it's Lagrangian and Eulerian coupled the method. So there's other code, but at the present time, we can access all this, but LS-DYNA is unclassified, unlimited. Just once you learn how to use a tool, this is all tool. Software is a tool, remember. But you can't say, I don't need a tool, then you can solve the problem. To build a beautiful home, you need a tool. You need a hammer. You need, what do you call that? The plane, tape, you know. You need nails and all that. So that's what this software does it. So some people say, oh, I don't like commercial software. Of course you do not like, but you can solve complex problem. Oh, I can program. Of course you can program, but has a limited scope it can handle. So submarine and surface ship, just think there is a few different classes of software. So if you want to know more, you may see me. Right now, I don't want to expose all my students many different code, then they suffer to learn all these different tools, no reason to do. I try to minimize a number of tools to build a beautiful home. So that's what I do. Okay, so there are a lot of pre-processing software and post-processing software, or both post processing software. So don't just pick up and use it. Once you pick up the software, then you have to invest lots of hours. And in my lab, in Yeonok and here Higyu, Chorong, and Chongwan, as I see them, they sweat, they spend a lot of hours, and now they are in the position they can handle the fluid structure system pretty well, including all the computations. So it's for me, it's feel better. Then I can really tell whether their results are meaningful, or their result makes sense, or result are garbage. I can tell. And now it's good because they suffer some time. They really spend the time and test out the tools using simple problems and so on. So computer code is unavoidable. And of course in our department, faculty member, they have their own code, or they have a different number of softwares, then they have to access and to solve it. Okay, I'm going to stop right here.